La. Right. It's bouncing. Very good. Let me begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I had an example to start us with here. So this is something you definitely don't want to integrate directly, right? Like 1 over a cubic does not integrate nicely. And on the other hand, this is not, I mean, our intuition is that this is kind of like p equals 3, the p equals 3 integral, right? So by comparison, it should converge, but how do we show that? So this one actually is pretty nice if we just convert this, making a u equals to x minus 2 substitution. See, if we make a u equals x minus 2 substitution, then x is equal to u plus 2. So x cubed is u cubed plus 6u squared plus 12u plus 8, right? And so that means that this is actually the integral from what? Instead of 7, we do what? X equal to, u equal to 5 to infinity, and du is equal to dx. So we've got du, x cubed minus 8 is what? U cubed plus 6u squared plus 12u. And the point here is that by making this substitution, I have gone from an expression where I have subtraction in the denominator, right, to a corresponding expression where I have addition. And why is that better? Well, that's better because then we can use like our basic trick, which is what? You know, this is less than the integral from 5 to infinity of du over u cubed going from here to here. Why? Since 1 over u cubed plus 6u squared plus 12u is certainly less than 1 over u cubed for what? U greater than or equal to 5. So by comparison, we can trade the integral above for the integral below. Yep. Because if we change the variable, we have to change the bounds. If x is equal to 7, then u is equal to 7 minus 2, which is 5. As infinity goes to infinity. Yep.
Why did you change the denominator? If you use that integral, you could just have it as simple equation x.
But if I subtract 8 and I just change it to x cubed, why would x cubed, 1 over x cubed minus 8? I mean, is it true that 1 over x cubed minus 8 is less than 1 over x cubed? That's the problem. Yeah. So I can't do that. That's the whole reason for me talking about this. And so, but then, so this converges what? I mean, this is less than infinity since it is the tail of p equals to 3 integral from 1 to infinity dx over x to the p, right, which converges. So therefore, that integral converges by comparison to the p equals 3 series. But you see, this is what I was trying to, I was mentioning this yesterday. I said you can make a substitution. It might be helpful, right? But it turns out the problem we were talking about at the end of the class, I don't see the substitution yet. If you look at the video from yesterday, I posted like a very short video after the class lecture video. And, oh well. And I give an inequality there, which would help with the problem we talked about at the end of class. So I just point you to that video, look at that. I actually give you, a gentleman in the back will agree with me, a significant hint on how to do that problem, right? Is that fair? You were there. Yeah? Agree, disagree? Okay. Or you could just ask him. He might charge you $1 or something. I don't know. What would you like your name to be today?
Sorry.
What would you like your name to be today?
Jim.
Jim? Okay. Hey, isn't that? Sometimes people ask me, do you mind calling me? Do you mind me calling you Jim? To which I always say, no, but I won't really recognize it when you call me. No one calls me that. But anyway, except people who don't know me. Which is rather ironic, right? Because people who call you Jim that don't know you are trying to like call you by something that people know you would call you by, right? Which is the great irony, because no one who knows me calls me Jim. So, okay. Now that example is out of the way, let us talk about finding our tails. Finding your tail. So the basic thing that we have neglected to give a name to so far is the tail. And so here it is. If we look at the sum k equals 1 to infinity of a sub k, all right, we can break that into the sum k equals 1 to n of a sub k plus the sum k equals to n plus 1 to infinity of a sub k. All right. Now I already gave a name. For this. What did I call this? This is the what? If we take the sum out to n, we said that this is the so-called nth partial sum, right? This is the nth partial sum. We call this S sub n as my notation, right? And so what remains, the rest of the series past n is called the tail. And I'll use t sub n, all right? You're just like, well, what is n? Well, n could be 1, n could be 2, n could be 3, n could be whatever you like. You can always take the series and like chop it somewhere and look at what comes before and what comes after, right? I mean, you can do this. What can you say? If the series converges, then what can we say about Sn? Number one, series converges means what? Sn goes to what? L, right? Some real number. What about Tn? What happens to Tn if the series converges? What has to happen to that last piece? Yeah, it has to go to 0. That's right. Both of these, of course, are as n goes to infinity. Right. 2, I'll just say this. If Tn does not go to 0, then the series diverges. Yeah? All right. So the picture I should have been drawing yesterday, and this is why I got confused, guys, is because I was drawing the wrong picture. If we look at the function which is, continuous, positive, and decreasing, something like this, and limits to 0, right? This guy. The picture I should have been thinking about starts at n. All right, so start at n. And then you can look at the area, look at the area under the y equals f of x, like this area, right? That would be the integral from n to infinity of, f of x dx. That we could compare to what? A couple different things, right? One thing we could look at would be, again, look at y equals f of x, where f of n is equal to a sub n, all right? So one thing I could look at would be these boxes like this, right? That are below the improper integral. This would be what? This would be an, this would be an plus 1, an plus 2, and so forth, right? So that would give me what? That's less than or equal to the sum, k equals n plus 1 to infinity of a sub k. You see that? For a function which is positive, decreasing. Whoa, that was cool. I saw that. That was not on purpose. Was that just like random?
Yeah, I wasn't expecting
He was messing with his pen, and all of a sudden, like I saw a piece of pen just go like whoop. It's cool. Oh, it's fine. As you know, I'm easily distracted. Let's see here. So, do something interesting in class to your own risk. Well, the risk of your peers mostly, because I will get distracted. But maybe that's what you want. So I don't know. Let's see here. Okay, so what's above the improper integral? I mean this one, right? This stair step. What's this? This is an, right? And then this one's an plus 1. This one's an plus 2, and so forth. That's clearly above the black, you know. And so this is an upper bound on the sum, the tail of the improper integral. In particular, this is the sum k equals n to infinity of a sub k, right? And so in my newfangled notation for the tail, what does this give us? This gives us a bound, right? I'll write it over here. Therefore, t sub what is less than or equal to the integral from n to infinity of f of x dx is less than or equal to t sub what? See, this is sum k equals n plus 1 to infinity, so I've defined that to be, this is Tn, is below. And then by definition, above, we have n minus 1. Yeah? Was there a question? What's the significance of the tail? I mean, you're like, well, it has to go to 0, great, but what does it mean? Conceptually, what does the tail mean? Notice that Tn is equal to what? It's equal to the full-blown series, k equals 1 to infinity of a sub k minus what? Solve for Tn. What do you got? You got the series from 1 to infinity minus the nth partial sum. So what is the tail? What's its meaning? Yeah? No? It is exactly what we were looking for last class, right, that I got stuck on. It's the error in the nth partial sum, right? It's the difference between the real, honest-to-goodness, full-blown series and just keeping the first n terms. That's what the tail is, right? So this is the error. Error in the nth partial sum. So looking over here, what does this do? What does this do? This is the error bound. I mean, it gives us an explicit account of what's the small, you know, like where does the error, where's the error fitting, right? So let's go back to the thing I got stuck on, the how to bound. Well, before we do that, actually, let's do something a little bit different. Let's take a harder look at the harmonic series. You know, because I've proved to you it diverges in a somewhat circuitous fashion. Let's just appreciate what the error bound says about the harmonic series, because the error bound applies both to convergent and divergent series, and we can really learn something concrete about the divergence of the. Let's study the divergence of the harmonic series a little bit more in depth. Right? Case study. So first things first, let's calculate the integral from n to infinity of, oh, shnikes. Oh, I'm sorry. I've neglected yet another thing. I mean, I need yet another picture, right? Because I can't, if the improper integral in question is divergent, again, this is meaningless, right? But there's yet another picture we could draw for this one, right? If we went, say, from, oh, and so I think this goes back to what I actually did yesterday. So here's, if we go from 1 to, say, 1 out to n, right? This, let's go back to this here. That would be the integral from 1 to n of dx over x, right? That integral, I want to compare that to what? That's less than this, right? Which would be, that's less than or equal to what? 1 plus a half plus a third plus da-da-da-da plus what? We don't get to n, we get to what? 1 over n minus 1, right? Agree? So, great. This is what? This is the natural log of the value of x evaluated from 1 to n, also known as natural log of n minus natural log of 1. That's less than or equal to the sum, k equals 1 to n minus 1 of 1 over k, right? But the log of 1 is 0, so we have the following. Natural log of n is less than or equal to the sum, k equals 1 to n minus 1 of 1 over k. If you don't mind, I'm going to look at this. Well, I mean, it's fine. It's fine. So what does that show you? As n goes to infinity, what happens? What happens to log of n as n goes to infinity? Blows up, right? That means that you can make the partial sum of the harmonic series as big as you want. Suppose you wanted to find how many terms in the harmonic series would it take to, say, get to 10. If you want the partial sum, suppose you want, partial sum of, at least 10, how far should you go? Right? In other words, I want 10 to be less than 1 plus 1/2 plus 1/3. I mean, to match my estimate, I guess I should put an n minus 1 here. So, like, I can do what? I can just look at, if I make 10 equal to the log of n, that'll do it, right? If I make 10 equal to the log of n, that means that the sum k equals 1 to n minus 1 is less than, 10 for that n. What is that n? Looks like I could use n equals e to the 10th, yeah? How big's that? So I did some number crunching before class. E to the 10th is 22,027, roughly speaking. Now I did some more I did some more number crunching, and let's see here. Oh, actually, I didn't figure that out. Now, that doesn't mean it actually takes, it doesn't mean you actually have to go 1 plus a half plus a third plus da-da-da plus 1 over 22,027 to get to 10. In fact, you're going to get to 10 before that, right? That's just, by the time you get to the 22,027th partial sum, well, 26th partial sum, you're definitely at least 10 in the partial sum is what this says, right? Fun facts. If you look at the sum, let's say k equals 1 to big N of 1 over k, here's some different values for you. If you put n equals to 1,000,000, the millionth partial sum of the harmonic series is 14.39. That's not too bad, right? What's the billionth partial sum? It's about 21.3. In order for the partial sum, to get to 20, if you want this to be about to get to 20, excuse me. Let's see here. Oh, what if you wanted to get 100? If you wanted to get to 100, if you want the partial sum to be about 100, guess what you need, roughly speaking, how many terms do you need? What big N do you need to get the harmonic series to reach 100? How many terms do you have to take in the series? Roughly. And this is actually, well, okay, so if we take e to the 20th power, we get, if you took e to the 20th power, you actually get 485 million, but actually it reaches 20 at just about 275 million. So, if you were just to try to see if the harmonic series was diverging with your calculator, it could be very deceiving. Because if you just keep adding terms, it doesn't seem like it's growing that fast. And you might think, oh, well, maybe it's just calculator mistake or something, right? Maybe it's really going to settle on some value eventually, but it never does. It just keeps growing, right? Like a logarithm to infinity. But it does so very, very slowly. See? Yeah. Any questions? I just thought it would be, at times it's good to do some numerical investigations, and that's what this is. Yeah.
Wait, for that last thing, does e to the 20 give you 100?
Oh, e to the 20 actually gives you about 4.85 times 10 to the 8th. So, what the theorem would say is that the sum k equals 1 to e to the 20 of 1 over k, that the natural log of e to the 20, which is 20, is less than or equal to that. So if you actually go to the 485 millionth partial sum, it's bigger than 20 by a little bit. In fact, it's actually .58. So, of course, I'm using Wolfram Alpha, right? You could use MATLAB or whatever to calculate these things. Don't recommend doing it by hand. Yep. Well, 1 billion is 1,000. It's 1,000 million. Did I miss a zero? Oh, yeah, I'm sorry. I see your... I'm sorry, I see what you got. You guys are right. I copied something down wrong. Oh, yeah. To get to 100, if you wanted to get to 100, it's much worse. To get to 100, you need something like 2.7, and this is more than enough. I'm not sure how much more it is, but certainly by the time you get to 2.7 times 10 to the 43rd, you get to like 100. I don't think I checked on how much an overestimate that is, but slow growth, right? Not a good investment, right? Some would argue better than gold. Whatever, I don't care. Okay, so going back to my previous example, so if I look at the sum, k equals 1 to infinity of 1 over k squared, right? That's 1 plus a fourth plus a ninth, yeah? Dot. And so my question was, if I just use this would be S3, right? Which is what? I was too flustered yesterday to actually calculate it. What is it, though? 1 plus 1/4 plus 1/9, 49/36. I really want a decimal here. Approximately 1.361 repeating. I'll keep 4 decimals just for the sake of. So my question is just this: what's the error? Can you bound the error in this? So I struggled yesterday because I didn't have the right tool in hand. The right tool is the bubbled thing over here, right? What are we trying to bound? What's the error in S3? T3, right? We're trying to say T3, the tail, using the third partial sum is how big is it? So what do we have? We have that T3 is less than or equal to the integral from, what is it? 3 to infinity of dx over x squared, but that's easy to calculate. That's the limit as t goes to infinity of, minus 1 over t plus 1 over 3. Right, because the integral of 1 over x squared is minus 1 over x. I evaluate at the upper bound t, I get minus 1 over t. Lower bound gives me a minus a third, which is 1/3. Of course, the t term goes to 0, and what are we left with? We're left with 1/3. So that tells us that if we use the third partial sum for the p equals 2 series, we're within 1/3 of the answer. S3 equal to 1.3611 is within plus or minus 0.3333 of the p equals 2 series. Since we've done this much, let's figure out what would the error in the fourth partial sum be? What would S4 be? Actually, let's be even greedier. What would the error in the nth partial sum be for the p equals 2 series? I think you can see here that Tn, right, is less than or equal to the integral from n to infinity of dx over x squared. For this example, we can straight up calculate that. Almost the same calculation, right? Gives us back what? Instead of 1 over 3, we get 1 over n, right? So what that tells me then is that Sn, which is 1 plus 1/4 plus 1/9 plus plus 1 over n squared, if I look at the p equals 2 series, the sum, k equals 1 to infinity of 1 over k squared, minus this nth partial sum, right? That's less than 1 over n squared. So you guys, if we wanted to calculate the p equals 2 series, to say within 0.01 of the true series, how far would he have to go? This is a question we could ask and answer, right? Does that make sense? Let me write that question down. What n gives error of at most 0.01? The marker's worthless. Yes?
I think somehow for us to how on the right side of that inequality it's 1 over n squared instead of 1 over n.
Oh, yeah. How did I get to 1 over n squared on the right side of that inequality? Can anybody tell her? Follow the man. There you go. So, yeah. Oh, man. I'm way off. I was robbed. Yes?
So like for the error you did in example 2, you only did like, I don't understand like why we only do Tn is less than or equal to like the integral, because where does the Tn minus 1 go? Like, so you have to do the right
Oh, it's
one.
still up there. We just don't care about it.
So like how do you know it's plus or minus then? Like, because you only did like the left side of the bound, right? Like T3 is less than or equal to the integral. Like you only did the left part of the bound, right?
Hmm. I mean, we could take absolute values of, that's what I did here, you notice? Let's see here. Let's see here. This has to be less than or equal to, no. I guess I don't know that for sure. Let me think about that more. That's a good question. So, getting back to this one, assuming that there's not something deeper in what he just asked about, what should I make n here? What do? You just put 0.01 and set it equal to 1 over n, and what's that tell us n should be? What's 1 over 0.01? Oh, looks like 100, right? So if we use like the 100th partial sum in this case, we should get within about 0.01. All right. Yeah. Let's see here. Oh, so I must go on. Anyway, I just wanted to return to that. So does that make sense at least? If we want to find a bound, we can just calculate the if this integral is something we can do, that allows us to put a bound on the size of the tail. But the tail is the error, so that means that we're within that far of the answer. I'm trying to think in words, what does this do for us? It does something, right? What's that mean? Well, this says that, I mean, if this is true, what does it say? This says that the error is what? Is it decreasing? Thank you. I mean, the error is what? It's getting smaller, isn't it? And so this is quantifying, I don't know. I'm not sure what to say about that. There's something to say there, but I'm not sure what to say. Let us go on now that we found our tail. So, fortunately, just one tail to worry about here. Yeah. So what I'm going to try to do, guys, is I'm going to try to forge ahead and present the rest of the convergence and divergence tests today, if at all possible. I'm not sure if I've already spent too much class time on this, probably, but I'm going to do my level best here to state a good amount of the convergence divergence theorems today. So let's get to it. So we already have the integral test, but why is the integral test a little bit scary? Because what? We have to integrate, right? So that's kind of a hard, a big ask, using the language of current trend-setting business people. We also talked about the direct comparison test. In the handout, it's called the basic comparison theorem on page 589 of the chapter 12, section 12.3 in Salas and Hilly. The next up is the limit comparison theorem. All right, or as I would call it, LCT. All right, and here's what it says. Let the sum over AK and the sum over BK be series with positive terms. If AK over BK goes to L as K goes to infinity, and L is positive, right? Then the sum over AK converges if and only if the sum over BK converges. This is so much nicer than the direct comparison test because you notice what's conspicuously absent here is a what? An inequality, right? We don't have to supply an inequality to compare the two series. We can just look at the limit of their quotient, and that tells us. So the proof of this is as follows. So we'll suppose that AK and BK are positive, all right, with AK over BK going to L as K goes to infinity, all right? So what he says is okay, so for some K sufficiently large, say K greater than or equal to K naught, all right? We have the absolute value of A sub K over B sub K minus L is less than epsilon. All right, so I would say this, for epsilon greater than 0, there exists K naught. So when K is larger than that K naught, we have that the difference of a sub k over b sub k minus L is less than epsilon. I mean, why is this? This is what it means for the limit of ak over bk to go to L, right? This was their definition of limit. That means that we can make the limiting value L arbitrarily close to the thing being limited, which in this case is ak over bk. But what does that tell you? What does this mean? This means that minus epsilon is less than ak over bk minus L is less than epsilon, right? That's what that inequality means when we unwrap it in terms of a double inequality. And then that, you could do what? Add L to both sides, right? L minus epsilon less than ak over bk less than L plus epsilon. Oh, but then one more step. What do we get? bk times L minus epsilon, right, is less than ak is less than bk times L plus epsilon. Why do I know multiplying by bk doesn't change the order of the inequalities here? What did we assume about bk? It's a positive series, right? Fantastic. Now, what? Let me give this thing a name. Let's call it star. What good is star? So if the sum over ak converges, then what does that say? That says that the sum over bk times L minus epsilon converges, right? I mean, to be fussy, I'm assuming that epsilon is not too big, like epsilon is a small positive quantity. I don't want L minus epsilon to be negative. And I can certainly I can make epsilon small enough such that L minus epsilon is positive, right? So L minus epsilon is just is a particular number. And what did we prove? We proved that a series converges. If you take a scalar multiple of the series, it still what? Still converges, right? Like multiplying by a number doesn't change the convergence or divergence. So how do I know that this converges? What am I using? I'm using the what? Direct comparison test, right? So the direct comparison test implies the limit comparison test, in fact. What about the other? What if the sum over a sub k diverges? Then we have the other. So this time I have an answer to your question. You'll be asking me where do we use both sides of the inequality, right? So I use the left-hand side to get the convergence. I'm about to use the right-hand side to get the second. Like this right here tells me that a sub k diverging implies that the sum of b sub k times L plus epsilon diverges. Again, by the direct comparison test, all right? So that's the theorem. This is the limit comparison test. So I think it's important for you guys to see proofs because it doesn't take actually that much time. And I don't think you should look at these things as a black box. You should try to appreciate why they're true a little bit. But of course, you're Calculus 2 students. The thing you're primarily responsible for is using these theorems, right? So let's focus some time on that. So let me find an example here. So I will, rather than using the examples in the book, which are great, I'm going to go to the end of the section, see if I can pick a problem. Some k over k cubed plus 1. All right. To me, this is sort of like what? This is sort of like a p equals 2 series, right? What does this mean when there's no lower bound given? I mean, that doesn't really concern us, right? I mean, you could put k equals to what? Whatever you like, k equals 0 to infinity, sure, whatever. So here's let's identify a sub k is k over k cubed plus 1. And we're going to compare to b sub k equals to 1 over k squared, right? As we know that the sum k equals 1 to infinity of 1 over k squared converges by p equals 2 series result, right? It's a p equals 2 series. We proved that converged last time, right? So what's a sub k over b sub k look like here? We have to do some algebra. We get ourselves a k cubed divided by k cubed plus 1. Let's divide the top and the bottom by k cubed. What does that give us? One over 1 plus k cubed, right? So as k goes to infinity, you can clearly see this goes to 1, right? As k goes to infinity. So therefore, I'm going to call the original, therefore the sum, k over k cubed plus 1 converges by limit comparison test with p equals 2 series. All right? Should we look at another example? Let's see here. I actually like his example. Why fight the power? Example 7 is actually pretty good from the textbook. I'm gonna look at that one. Sum k equals 1 to infinity 1 over 5 to the k minus 3. Again, the question always, and I keep forgetting to ask this question, but it's always the question we're asking at the moment, is does the given series converge or diverge? All right? So does the series converge or diverge? Well, my intuition when I look at this is like, this is almost 1 over 5 to the k. And we know that the sum k equals 1 to infinity of 1 over 5 to the k is what? This is 1/5 plus 1/25 plus 1 over 125 plus dot, 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 dot. In other words, this is geometric series with what? A equals to what and R equals to what? Well, the first term is a fifth, so I'll pick off the A. A is 1/5. Remember, A is the first term in the geometric series. How do you get the next term past that? Multiply by what? 1/5. Yeah, I mean, A and R are the same thing. They're both a fifth here. So this converges to what? This converges, in fact, to 1/5 over 1 minus 1/5, right? Which is A over 1 minus R. Because, the r is equal to 1/5, and that's less than 1, right? So we have a positive radius ratio for the geometric series less than 1, so we prove that that converges. Not only does it converge, we can calculate what it converges to. Great. Now, that's not the given series, though, right? But it's a lot like the given series. So I think, and why is direct comparison kind of a drag here? I mean, we can't do direct comparison because of the minus, right? The minus is cramping our style for direct comparison. But no problem for limit comparison. Is this a positive term? I mean, let's plug in k equals to 1. What do we got? K equals 1 gives me 5 minus 3, which is a half, right? What k equals 2 gives me what? 22nd, yeah. And then plus 1 over, what is it, 122. So it should be clear enough that that's a series with positive terms, so we can apply the limit comparison test. And let's compare to something we know, which in this case, 1 over 5 to the k. So let's see here. I'm thinking a sub k equal 1 over 5 to the k minus 3, and b sub k is 1 over 5 to the k. So consider ak over bk is, what is it? It's 1 over 5 to the k minus 3 divided by 1 over 5 to the k. Do algebra. We get 5 to the k divided by 5 to the k minus 3. By the way, if you don't like writing k, switch to n. It's not a big deal, right? Anyway, if I divide the top and the bottom by 5 to the k, I get what? I get 1 over 1 minus 3 times 5 to the, well, 3 divided by 5 to the k, right? And that goes to 1, right? As k goes to infinity. Yep.
The question is, how are you determining b of k?
How am I what?
How are you determining b of k exactly?
Oh, yeah, I don't know. How do you determine the b of k? That's a good question. That depends on the problem. It may or may not be possible to even find such a thing. The question is, what convergence or divergence test should we use on a given series? That is the deep and looming question that looms over everything we're doing. How do you choose which method to use? That is a hard question to answer in general. Here, my intuition was, well, if k is large, it looks kind of like just 1 over 5 to the k, so maybe I should compare to that.
You just using a similar term.
Right. Yeah. So as k goes to infinity, that goes to 1, which means, therefore, by limit comparison test, we find S converges since the sum k equals 1 to infinity of 1 over 5 to the k converges. And I like to do this. I'll give this a label so that I don't have to write it out again. I'm calling this thing S. Okay. So that is limit comparison. The next two tests, the root and the ratio test, a little bit different. So here it goes. So here's the root. I'll start with the root test. This is section 12.4. All right. So I think his question about which test to use is a good one. And part of the reason I'm not doing an in-class exercise yet is because I want to make sure we get through all of the tests first. Then I'm going to put problems up on the board and let you guys try to decide what's the right tool for them. Because there's an artificiality of looking at examples until we get all of the tests, right? Once we have all of the tests in front of us, then you get a better sense of, do you understand what you're doing? See, because There's a lot of different tools to use, and a large part of the mental effort in this part of the course is deciding which tool is right for which job. All right, so let us forge ahead here. Let some AK be series with non-negative terms. What's non-negative mean? That means that a sub k is greater than or equal to 0. It could be 0. Non-negative allows for 0. And suppose that a sub k to the 1 over k power, what, goes to rho. Then there are 3 cases. Case 1, if rho is less than 1, then the series converges. 2, if rho is greater than 1, then the series diverges. All right? I refuse to write case 3. This is the only part of mathematics wherever you find textbooks writing what doesn't work. But case 3 says that if rho equals to 1, you don't know. If rho equals to 1, the test is inconclusive, all right? I'm not going to write that down. So here's the proof. Suppose that, a sub k to the 1 over k goes to rho as k goes to infinity, right? And assume we're in case 1, all right? Assume rho is less than 1. He says choose a mu such that rho is less than mu is less than 1. All right? Now here's what he says. He says that if we look at a sub k to the 1 over k power, that's going to be less than mu for k sufficiently large. Does that make sense? Let me just write off to the side what we have control over, right? We know that if epsilon is greater than 0, right, we can choose k naught in the natural numbers such that whenever k is greater than or equal to k naught, that implies that the absolute value of a sub k to the 1 over k, right, minus rho is less than epsilon. So if I draw a picture here, the number line, here's 1, right? Over here is rho, right? Here is mu. Mu is somewhere between 1 and rho. And where is a sub k in this? We can make epsilon like this, right? So in this picture, where's my a sub k to the 1 over k? It's like, somewhere in here. It's within that epsilon distance from rho if we make k go far enough out. So you see why that says? You see that it then should be clear to you why this inequality is true, right? So the a sub k to the 1 over k has to be close to rho